Hi everyone, I'm Tan Xu, and my topic is about inviscid and incompressible flow around airfoil. This is how I did the project and also the process of my presentation this time. This is my problem, and in the center there is an airfoil, and boundary conditions, governing equations are all in the picture, and I will solve the potential flow and compare the results with answers. And also I would change the angle of the tag to see if there's any difference in the solution. And this is the geometry. In front there is a half circle and the tail is 5 meters long. I use the answers to mesh because it's automatic calculated, so I used pretty intense meshes. Extracted the information about the nodes and elements and exported them into my MATLAB. At first I didn't know that even if I choose to mesh with quadrilateral elements, there could be some triangle elements within them. And I got some very strange answers. After correcting the problem, I got my answer, and we can see that the flow is flowing from the left to the right. And that's the potential lines in the field. And we can see the lines is perpendicular to the surface. It's my flow vector field, and the velocity is calculated by the equation on top. The derivatives of 4-node quadrilateral elements and 3-node triangle elements are not continuous. So, at some positions, especially when the velocity changes dramatically near the stagnation point, we can see some discontinuity. These vectors are calculated by every element near the point. So near the tangent point, we can see several vector directions. When I used more intense meshes, and we can see the problem is improved, but the discontinuity cannot be eliminated. And this is the streamline around the airfoil, and streamlines are tangent to the velocity vectors. This is the pressure distribution, and it is calculated by Bernoulli equation. And we can see the pressure near the stagnation point is the highest. This is the pressure coefficient, and it's based on Bernoulli equation, and it can be used to calculate. And then I wanted to compare my solution with the solution of answers, but the answers cannot set the viscous to be 0, so I wanted to compare the solution about heat transfer problem. The governing equation between heat transfer and potential flow are similar. The definition of gradients are different. And you can see the distribution of scalar. The vector field are quite same. All the directions are kind of identical, but my solution didn't show the magnitude. These two pictures are the streamlines with different angles of tag. But my solution are not quite right. The stagnation point must be at the trailing edge, which is cutoff condition, and I'm still looking for the way to solve it. Though I didn't perfectly solve the problem, but the experiences I learned from the project are the most valuable. Thank you.